So now it's my pleasure to introduce our guest speaker this evening. It's a particular pleasure this evening to introduce to you Professor Thompson from Bath. Over supper, he told me a little bit about his career. It's quite magical. He spent rather a lot of time in Yorkshire, but we'll forgive him for that. Went to Liverpool, Loughborough, and is now at Bath. He has this fascinating interest into the particular discipline that he's working in. And when I looked at it, didn't know where the Milner Institute was. So I had to look it up, to be frank. And I was quite fascinated by what I read, because it's a multidisciplinary institute that embraces biology, health, and education. It has some specific challenges, which I hope he's going to lead us through. That is the evolution of it all and the evolution questions. It's challenged apparently to find new technologies and clinical evaluations and applications. I look forward to hearing a little bit about that. And it's also to take research into the community. And that's possibly one of the reasons why he's here this evening, to try and persuade us. Because looking at our age, looking at the topic, it seems very apposite that we're going to enjoy it this evening. But the real thing that amused me somewhat is the other adage behind the Institute. And it said that scientists need natural light, space to socialize. And if you've ever seen their building, it certainly fulfills those criteria. But most particularly, it has to have good coffee. Anyway, without much ado, let's get on. The floor is yours, sir.
Okay. It's a great pleasure to be here. Thank you ever so much for the invitation to talk tonight. So yes, just a little bit about me before we get into the substance of the topic. So yes, I'm a professor of human physiology, so I'm a physiologist by background. I'm part of the Milner Centre, but I'm also one of the directors of what you can see here on the top left, which is the Centre for Nutrition, Exercise and Metabolism, which we abbreviate as CNEM. So we have an interest in physical activity, exercise and nutrition in particular. It links to evolution. I will touch upon that later on. And just by means of a little bit of background, we've been working on different aspects of physical activity for the last 25 years at Bath. I was one of the members of the most recent update to the physical activity guidelines here in the UK in 2019. So I like thinking and talking about physical activity, and it was very much my pleasure to come and talk to you about it tonight. So yes, some of what I'm going to say tonight isn't exactly new. Here's a quote from Hippocrates well over 2,000 years ago, emphasizing the importance of exercise for good health. And several centuries later, another ancient Greek physician, Galen, summarized it even more neatly. The body is in need of motion, exercise is healthy, and rest is morbid. So in ancient Greece, there was already recognition that physical activity is a fundamental component of good health. If we fast forward to today, to the 21st century, here's a quote from the previous outgoing chief medical officer, who stepped down literally the month before COVID hit. So they dodged a major responsibility. But at the same time, perhaps doesn't have quite the same household name as Chris Whitty. But here's a quote from Dame Sally Davis, who said, "If physical activity were a drug, we'd talk about it as a miracle cure." And the reason that people are saying things like this is because we now recognize that physical activity affects essentially every single cell and system within our body. This is just an illustration which comes from this resource here, which is actually a wonderful text. It's aimed primarily at GPs, at doctors, trying to communicate the role of physical activity and good health. And it does a really, really good job of making the contemporary information very, very accessible. But physical activity has widespread effects throughout the body. And that's a really important point, and I'm going to come back to that later on. And the effects are substantial. We're talking about a risk reduction in many common illnesses and diseases of 30 to 50%. So it's not a trivial effect. It's a very, very substantial effect. And this is recognized now internationally. So here's a quote from the World Health Organization based on their evidence analysis, identifying that physical inactivity, so the lack of appropriate or sufficient activity, has been identified as the fourth leading risk factor for global mortality. So a key question, I suppose, I'm hoping you're asking as people interested in science is, how do we know these things? The ancient Greeks were talking about it thousands of years ago. They were speculating at that time based on their observations. What evidence do we now have to support some of the statements that I've already made from people like the Chief Medical Officer? So I just want to briefly go through some of the different types of evidence and the different approaches which have led to the kinds of statements that I've introduced. And the first kinds of studies that I want to touch upon are some of the epidemiological studies which support a role for physical activity and good health. And actually, the first ever epidemiological study which connected physical activity to health was actually conducted here in the UK. It was conducted by somebody who's very well known in my field, somebody called Jerry Morris. And for context, this was done in the 1950s when there was what was seen at the time as an epidemic of cardiovascular disease. Many, many people were dying from heart disease, but people didn't really understand why. They didn't understand the root causes. And Jerry Morris did what was a very simple epidemiological study by today's standards. He examined cardiovascular disease risk in London bus workers. And he identified an opportunity here because the London bus workers, the drivers, were sedentary because of the nature of their job. And as many of you, I'm sure, will remember at the time, the bus conductors were on their feet all day, going up and down the stairs, taking fares from the customers. And what he found was that the rate of coronary heart disease episodes in the bus conductors was less than half that of the bus drivers. And so this was the first epidemiological evidence that physical activity, in this case, physical activity of work, is associated with a lower risk of heart disease. And this has been supported now by literally thousands of epidemiological studies which show this kind of relationship. I just want to pick one other just to kind of illustrate how the epidemiology has moved on. This is a very large epidemiological synthesis of over 500,000 people followed up over a very long period of time. And what they did to move beyond what Jerry Morris did is they started to try to understand dose response. So here we've got a graph showing mortality risk on the left-hand side with increasing measures of physical activity volume over a week. It doesn't matter so much about the units. We can come back to that later on. But what you can see is that there's a progressive decreased risk as you increase levels of physical activity, so that when you get to roughly this point, there's around about a 40% decrease in mortality risk associated with that level of physical activity. So we have epidemiological studies which consistently show that physical activity, higher levels of physical activity, are associated with improved health outcomes. We also have mechanistic interventional evidence to support the epidemiological evidence. So we have studies like this one, which is an animal study. This was a study conducted in monkeys. It was probably the most substantial of and most relevant of animal studies, which is why I've picked this as an example. What they did is they created two groups of animals that were studied over a 2-year period, so it's a very long study. One group of animals were forced to become sedentary, the other group of animals were forced to become active. And what this image shows is a cross-sectional slice of their coronary arteries. So this dark grey here is the coronary artery. This is the center of the lumen or the vessel. This white is the bit which is still patent. This light grey area here is the atherosclerotic plaque. It's the development of heart disease in these animals. In the active animals, you can see that there was very little atherosclerotic plaque, very little heart disease, and also the size of the vessel is also much bigger. So we have direct evidence from animal studies to support these epidemiological studies to understand exactly what's going on. In humans, we don't have that kind of causal evidence, but we still have causal evidence, evidence from intervention studies, randomized controlled trials in humans. One key point is that we're not going to look at coronary arteries directly, of course, in humans. Instead, we rely on risk factors and changes to cardiovascular risk factors. And I'm not going to go through all of the studies because, again, there are literally hundreds of those studies now. So I just wanted to pick one example. This shows a meta-analysis of randomized controlled trials looking at changes in blood pressure when people took part in an exercise intervention. So each one of these references here relates to an individual randomized controlled trial. This is the data for systolic blood pressure. These are the data for diastolic blood pressure. These are the results for the individual studies, and this is the average effect across all of those studies. So based on this meta-analysis, systolic blood pressure decreased about 11 millimeters of mercury. Diastolic blood pressure decreased about 6 millimeters of mercury. And I just want you to remember those figures for a moment. So 11 and 6. Because this effect from this meta-analysis across randomized controlled trials is about the same as the effect of a very common medication which is given for people with high blood pressure. So a lot of people receive ACE inhibitors, which relax blood vessels to try to decrease blood pressure. These are the data for a common ACE inhibitor. This shows the change in blood pressure with an increasing dose of this ACE inhibitor. The green is the recommended dose or zone. And if you look at the average effect, the decrease in diastolic blood pressure, 5 to 7 millimeters of mercury, the decrease in systolic blood pressure, 8 to 12 millimeters of mercury. So the effect of exercise across the meta-analysis on blood pressure as a major risk factor for heart disease is about the same as this particular medication in terms of the size of the effect. But of course, one of the other advantages of physical activity and exercise is that unlike some of the side effects that you might get from some medications, the side effects of physical activity or exercise are lots of other good stuff. So you're not only reducing your blood pressure, but you're also going to be affecting many other physiological systems at the same time. So we have evidence from epidemiological studies, we have animal evidence, we have evidence from randomized controlled trials looking at risk factors associated in this case with cardiovascular disease. We also have evidence from quite novel interventions in humans looking at a physical activity reduction, so taking physical activity away. And we've been part of one of these studies. We were very fortunate to be part of one of these studies. It was conducted and led by the European Space Agency. It took place in Toulouse. And it was all just in men in this particular study, but it involved 20 young men lying down in bed in this position for 2 months. And they had to stay in bed every minute of the day. They had to eat in bed, they had to go to the toilet in bed, they had to have a shower in bed, they had to stay in that position for a full 2 months. And we were interested in a variety of different measures. It was a large collaborative team effort. But just to summarize the effect of that, I mean, this is a nice review which goes through some of the kind of major outcomes, looking at the effect of bed rest and the various kinds of changes that you get associated with bed rest. So they've been fed what they need, they don't gain any weight. All you've done is taken away the physical activity, and you generate metabolic inflexibility, metabolic syndrome. We've essentially turned these young, healthy men, aged in their 20s, into what are middle-aged or older men from a metabolic perspective in the space of 2 months. Now, this is being done because bed rest is a surrogate of spaceflight. The loss of adaptations that you see with bed rest are very similar to spaceflight, and the European Space Agency are interested in putting in place mitigation strategies to try to stop some of those changes from taking place. We wouldn't normally be able to do such a study, so it was nice to be part of that. But the key take-home message from this first part of my talk is that based upon a variety of different types of evidence, epidemiological evidence, mechanistic evidence, looking at different physiological systems and so on, we can absolutely conclude that physical activity is important for many different aspects of health. And I've just tagged this at the bottom, not just weight control, because so many people, when you talk to them about physical activity, they link it to weight. They, after Christmas, oh, I put on a bit of weight, I need to do a bit more activity. Or I've been on holiday, I've eaten too much, I need to do a bit more physical activity. Physical activity is not just about weight, and I'd love to talk to you about that later on if we have time. So, why is physical activity so important for health? It's absolutely demonstrably important. Why is it important? Well, a main reason is because our physiology expects it. For millions of years, we had to be physically active. Being active was associated with survival, with the procurement of food, with safety, with whether there was hunting or gathering. We had to be physically active. There was no choice. And so when the genes that make up modern humans were selected, they were selected in a backdrop of high levels of physical activity. Now, we don't have to go back very far in time to find a time where we still had to be physically active. We weren't active hunting and gathering, but we were nonetheless active, often through physical work. Of course, nowadays, we've engineered machines which can do the work of a large number of people with no physical activity or very little physical activity. We've done that in the workplace. We've done that in our homes. We've taken tools which involve physical activity or effort and energy expenditure, and we've systematically developed tools which remove the requirement for physical activity. So we've done it in our work, we've done it in our homes, we've even done it in our leisure. Now, I have to say, I haven't seen this in Somerset, Wiltshire, or Gloucestershire yet, but this was in the United States, but perhaps it's coming soon. Let's hope not. But a key point is we are expected to be physically active. So a perspective I would like you to think about is we are expected by evolution to be physically active. If we become physically inactive, we take activity away. At a fundamental cellular level, we see a failure to maintain gene expression, the expression of genes at the expected level, expected by millions of years of evolution, and that many of the genes which require or expect physical activity are the disease susceptibility genes. Now, I know that trying to understand this perspective and perspective of evolution is often very, very challenging. So I just wanted to try to illustrate this concept of time and this mismatch using this kind of analogy. So this is an aerial photo of the athletics track at the University of Bath. I want you to imagine that one lap represents the last 4 million years of our evolution, so it equals 400 meters. And if we start here on the start line, we were already bipeds at that point. We weren't like we are today, of course, but there are many more similarities than differences. We continued to evolve, and all of this time there was a requirement for physical activity. we're evolving, we're changing, we keep coming round. Probably around about here, early humans arrived, we continued to evolve. We were still probably hunting and gathering. We then started to introduce agriculture and civilizations and so on. But at all of that period of time, there was a requirement to be physically active. If we zoom in to the final straight and look at the end of this 400 meters athletics track, where the last 100 years represents just the last 1 centimeter of this athletics track. For 399 meters, 99 centimeters, we've had to be physically active. And then suddenly, through societal changes, we've engineered physical activity out of our lives, and there's no longer a requirement to be physically active. But the key point is that this mismatch has happened in evolutionary terms very, very quickly. We are not engineered, we're not designed, well, maybe not designed is the wrong word, but we're not made to be physically inactive, and yet modern societies have found ways to remove physical activity. So a take-home message is our physiology expects physical activity. So a lot of the time, again, when people look at studies and evidence and they look at things like, you know, this is the effect of physical activity, this is the effect of no physical activity, they often think of physical activity as the intervention, the treatment group. That's the people are doing something to affect their health. But actually, you should probably think of this the other way around. Physical activity is expected by our bodies. And so the not doing physical activity, that's the intervention group. That's the behavior which is not normal from a physiological perspective. So our body expects physical activity. So far I've talked a lot about physical activity, but I actually haven't defined what it is. And the reason for that is because there are some subtleties which we need to explain. So when we think of physical activity, if we look at modern day physical activity terminology, the classic definition, which is accepted by most people around the world, is that physical activity is any force exerted by skeletal muscle that results in energy expenditure above resting level. So it spans everything from me just standing here today, all the way through to extreme ultramarathons lasting perhaps several days. So that's a definition of physical activity. Exercise is a conceptually different thing. Exercise is a subcomponent of physical activity that is planned or structured. So perhaps if you're going to an exercise class, or if you're doing some kind of structured sport, or you're going for a run, those things would be classed as exercise, which is a subcomponent of physical activity. And the reason for those distinctions, why I'm making those distinctions now, will become clear in a moment. We can measure physical activity using a variety of different kinds of devices. We use this research instrument. It's called an ActiHeart. They're very expensive. They cost £1,000. They're quite sophisticated devices, but they give you really good information about a person's physical activity. So here we've got energy expenditure, just expressed here in kilocalories per minute, over a 24-hour period. So this is sleep. So this is close to resting energy expenditure. But of course, if you get up a bit or turn around, you will increase your energy expenditure for rest. That's physical activity. You get up at the start of the day. And then this is the ebb and flow of physical activity energy expenditure over the course of the day. On this particular day, there was no exercise. This is just physical activity of daily life. Now, if you go to Google and type in physical activity into Google and look at images, these are the images that you get. You get images actually of exercise, not of physical activity. You get people running or weights or playing football. You don't get all the other forms of physical activity. So we asked the question a couple of years ago, well, how important is exercise compared to physical activity? What is the effect of structured exercise, an exercise program, on overall levels of physical activity. So conceptually, we designed a study where we recruited, in this case, sedentary middle-aged men from around the Bath area, and we put them on an exercise program for 6 months. And it started off with a structured bout of exercise 3 times a week, and eventually it built up to them doing structured exercise 4 times a week. We used the devices I've already mentioned, these ActiHearts, to measure how much energy has been expended in the prescribed exercise, the exercise that we'd asked them to do. And we could pull out the data for how much energy was expended through the prescribed exercise. But we could also pull out the data for non-prescribed physical activity energy expenditure as well. So we could look at the impact of the prescribed exercise on overall physical activity energy expenditure. And these are some of the key results. So there's quite a lot going on here, but this is just physical activity energy expenditure. So all energy expended through physical activity. The white bar is the control group. The dark grey bar is the intervention group. These are the data at baseline. The blue represents the amount of energy expended through the prescribed exercise intervention. Now, by week 18, they were exercising 4 times a week for an hour each time, so 4 hours of exercise a week, and they were working at what we classed as a vigorous intensity. It was 70% of their maximum oxygen uptake, if that's something you're familiar with. And the key point is that this only increased their physical activity energy expenditure relatively modestly. It only increased their, as a proportion of their total energy expenditure, only increased it by around about 7%. Now, most people would probably think if you're going to the gym 4 times a week, working extremely hard for those 4 hours, it's probably going to increase your overall physical activity and your energy expenditure by much more than that. So a key point I want you to take home as well is that exercise and physical activity are different things. If we only look at what we're doing during exercise, so we just take out what we did in the prescribed exercise intervention, then we get a picture associated with that exercise. But it's not until we look at overall levels of physical activity that we really start to get a sense of what the picture really looks like. So a focus on exercise, which is what a lot of people think about, misses out on the bigger picture. When you think of physical activity, you shouldn't be thinking necessarily about things like this. Instead, you should be thinking about many of the incidental things that you might do as part of daily life. For most people, even some of our sport and exercise science students, for most people, this incidental physical activity will actually be quantitatively much more important than the physical activity they're doing through structured sport. Another kind of way to think about this is just thinking of the temporal aspect. If you exercise 2 to 3 hours a week, you can see what a small fraction of a week that actually represents. Whereas if you think of instead waking hours as a movement opportunity, you can start to understand how it would be much easier and potentially more significant to change physical activity over a much longer period of time than trying to do an enormous amount in the space of 2 to 3 hours a week. So a kind of key take-home message 3 is it's important to consider all physical activity, not just to focus on exercise. When you think of images of what physical activity means, don't just think automatically of people in lycra in a gym or on a bike or something like that. It's much, much more than that. So hopefully I've introduced you a bit to physical activity in broader terms, some of the evidence base, the types of evidence that we've got. What I want to do now is just to shift tack a little bit and to focus specifically on the role of physical activity in healthy aging. So this slide I've already shown you actually conveys some of the most important information. Many of the illnesses and diseases that I showed you earlier on in this slide, which come from this really, really nice review, are age-associated illnesses. And so hopefully you're already starting to understand that by affecting the likelihood of developing these illnesses, you're showing and understanding how physical activity is impacting on health. But rather than just going through each of these illnesses in turn and focusing on the evidence base, what I want to do instead is to focus on just a specific part of the body, which is fundamentally important as people get older, but could also explain why and how physical activity is creating these effects throughout the body. So I just want to focus in on skeletal muscle for a little bit. So muscle is extremely important for function, for the maintenance of independence as people get older, for a good quality of life as you get older. And we'll talk about that a little bit later. But the other thing is that physical activity, when you contract it, is responsible for doing some really amazing things. Your muscle secretes molecules, literally hundreds of molecules, and we're just discovering more about these all the time. They're called myokines. They're released by working skeletal muscle. When you contract the muscle into the circulation, they make their way throughout the body and exert effects in other physiological systems. Muscle is also responsible for taking up and managing nutrients for things like blood glucose control, blood sugar control, for example. So muscle is not just about function, it's also much more than that. And unfortunately, as people get older, they tend to lose muscle. So this is just a cartoon showing a cross-sectional slice of the thighs. So here we've got the quadriceps at the front, the hamstrings at the back. This is a cross-sectional slice. This is somebody who might be 40 years old. A 70-year-old might have the same diameter leg, but actually it's made up of less muscle and more subcutaneous fat. And this is just a cartoon, and we'll go through some of the evidence in a moment. But typically what people estimate is that from about the age of 50, an average person will lose around 1% of their muscle a year after the age of 50. So a key question is, why do people lose muscle as they get older? And to explain that, I just first of all need to emphasize that muscle is constantly being turned over. And so when we give this lecture to some of our undergraduates and so on, we often emphasize that the muscle you arrived with in the room at the beginning of the lecture is different to the muscle that you leave with at the end of the lecture. It's constantly being turned over. You're making new muscle and breaking muscle down constantly. And you can measure those things using stable isotopes and skeletal muscle biopsies to get a measurement of something called muscle protein synthesis, or MPS, and muscle protein breakdown. And so over a typical 24-hour period, it might look something like this. So the blue is muscle protein synthesis. So you have a meal in the morning with maybe just a little bit of protein in it. You get an increase in muscle protein synthesis. It then muscle protein synthesis decreases. You have your next meal, it increases, and so on over the course of the day. And here you've got muscle protein breakdown changing over, or also over the course of the day. And the balance between muscle protein synthesis, the making of new muscle, and the muscle protein breakdown, the breakdown of muscle, will ultimately dictate whether your muscle mass gets bigger or smaller. So it's the balance between muscle protein synthesis and muscle protein breakdown. And unfortunately, aging impairs the ability to make muscle. Aging is associated with something called anabolic resistance. And this was the first study to report this finding. So I'll just explain what they did. It's been repeated many times since then. So they provided a drink containing protein to a group of young people and a group of older people, and they measured the synthesis of myofibrillar protein, so proteins within skeletal muscle in the quadriceps. And so you can see this is muscle protein synthesis here on the vertical axis. relative to the dose, the amount of protein that was given. And what you can see in the young group is this is the dose response in terms of muscle protein synthesis. In the older group, in response to the same amount of protein, there is a much lower increase in muscle protein synthesis. And even if you give a really high dose of protein, you can't increase it to the level that it would have been in the young people. So aging is associated with anabolic resistance. And so conceptually, what you need to think about is in the context of older people having less muscle, the reason why they have less muscle isn't because they're breaking it down. It's because they're not synthesizing as much in response to the same anabolic stimulus. So this is a review that Lee Breen is one of our collaborators. We're working with him today on projects related to this. This just shows muscle protein synthesis and muscle protein breakdown in young and older people. So if we look at the data for young people, muscle protein synthesis, you have an anabolic stimulus, whether that's exercise or protein in the diet, you get a big response in muscle protein synthesis, then decreases, big response. In older people, you get a much lower muscle protein synthesis response than you do in younger people, but the breakdown seems to be about the same. So older people have smaller muscles, not necessarily because they're breaking more muscle down, it's that they're not synthesizing as much in response to the same stimulus. Some of these data I've shown you so far were just in response to protein ingestion. You get the same smaller anabolic response in response to exercise as well. So this shows muscle protein synthesis in younger and older people to varying degrees of exercise. This was resistance exercise, and we'll talk more about that in a moment. So these are the data for older people, a much lower response than you do in the younger people. So the anabolic response to a stimulus is lower in older people. And one of the other really important things is that, unfortunately, if you have lower levels of physical activity, or if you reduce your physical activity, your general level of physical activity, that reduces your anabolic response. So we know that from this study from Lee. So what this study did is it didn't do a bed rest study like the study I showed you early on. It did a reduced activity model in older people, people older than 65. So what they did is they asked them just to reduce their step count. So I don't know if you can read that on here, but this shows step count. This is before the intervention and after the intervention. They were asked to reduce it to about 1,500 steps a day over a period of 2 weeks. In that 2-week period, they lost around about 0.5 kilo of muscle from their legs. So they lost a lot of muscle very quickly in their legs. And that loss of muscle wasn't associated with an increase in breakdown. It was associated with a poorer response, a poorer anabolic response. So this shows their muscle protein synthesis in the post-absorptive state. So that's when you haven't eaten anything. And you can see that was similar pre and post intervention. But what was different was the postprandial response to the response after ingesting a meal or ingesting protein. You can see that before the intervention, they had a much bigger muscle protein synthesis response than after the intervention. So again, this loss of muscle that you see with reduced physical activity, with lower levels of physical activity, is associated with a decrease in the ability to produce new muscle. And this potentially could have really important implications for aging trajectories over a person's lifetime. So this model shows what they describe as the catabolic crisis model of what might happen over a typical person's lifetime. So this is muscle mass on the left-hand axis over age over here. And most people lose muscle over time, as we've already alluded, about 1% a year after the age of 50. So you are losing muscle, and some of that will be because of this anabolic resistance. But on top of that, you might have particular periods of a person's life where something happens to them that reduces their activity for a few days or perhaps a few weeks. And as you saw in that previous slide, that will lead to a much more rapid loss of muscle. So the catabolic crisis model has people losing muscle, as you might expect, then something happens, whether they get injured or they get ill or they get sick, something takes them off their feet. You get a very rapid loss in muscle mass. It recovers a little bit, but never back to where it would have been. It then continues to decline and something else happens, an injury, something like that, hospitalization, and then you drop again and you never recover. And so by the end, or towards the end of a person's life, you might have a much bigger difference between where you would expect them to be and where they actually have got to. And so this lack of activity, taking away the stimulus that we expect, could have really important implications for the regulation of muscle mass over a person's life. And what I really like is that some very proactive healthcare boards and bodies are using this information to try to educate the healthcare workers and staff who work within their organisations. So this comes from the Northampton General Hospital. This was a poster. It's based on evidence, scientific evidence. 10 days in hospital leads to the equivalent of 10 years of ageing in the muscles of people over 80. So I think we can use this information to be very proactive about how we manage people over time. We could put things in place, prehabilitation strategies or rehabilitation strategies associated with periods of time where people have had to experience a reduction in physical activity. And maybe we can talk about that later on. So in terms of muscle and muscle mass and so on, this is the kind of model that people usually subscribe to. And within that, we can understand the impact of physical activity. So here you've got kind of functional capacity, or it could be muscle mass or something like that, depending on what you're interested in. Here you've got kind of normal aging, where you've got a decline in muscle mass and capacity. It is inevitable to at least some degree. But in some people, you might have accelerated aging, where, of course, you lose mass and function much more rapidly. It could be associated with illnesses or injuries. And, of course, that will lead to people passing thresholds for things like frailty and disability much earlier. We're actually working on a study at the moment to try to understand these different trajectories. It's called the ATOMA study. We're trying to understand why some people lose muscle mass more quickly than others. We suspect that some inflammatory molecules are particularly important. If you're over 65 and you feel like taking part, we are recruiting. We're about halfway through this study. So just drop me a line if you're interested. It would involve a couple of trips to Bath. So I understand that's a bit of a trek. But so we understand the importance of physical activity in terms of aging trajectories, but there is some very good news here. If you maintain physical activity or you increase physical activity, you can do a lot to regulate muscle mass. So these are MRI scans of people's quadriceps, just like I showed you earlier on with the cartoon. So this is a 40-year-old, this is a 74-year-old, this is muscle, there's the bone. In a 40-year-old, this is the 74-year-old muscle and the adipose tissue. But if you find extremely active older people, their quadriceps look remarkably similar to those of younger people. Now, this is an extreme example. This is a master's triathlete doing incredibly large amounts of training. But it shows as proof of principle that through at least very high levels of physical activity, you can maintain muscle mass. It's not purely an inevitable function of aging. But the other good news is that if you do have sarcopenia, if you have low muscle mass as an older person, a little bit of a very specific form of exercise, resistance training, which might be in the gym, but it could be using a band. And as I'll introduce in a moment, There are more innovative ways to do resistance training than that. But if you do resistance training, the effect of the resistance training doesn't diminish with age. You will still increase muscle mass in response to training. So this is a systematic review and a meta-analysis of randomized controlled trials. This is their conclusion. Resistance training is an effective treatment to improve both fat mass, muscle strength, muscle performance, and muscle mass in healthy older people with sarcopenia, with low muscle mass. And the other really good news is it's never too late to start. Here's a case study of a 105-year-old woman who had poor function and performance. She was prescribed an 8-week home-based strength training program with the help of a physiotherapist. And these are the changes that she experienced in just 8 weeks. She improved the ability to walk, speed, gait by 20%. She improved this standardized measurement of performance. It's called the SPPB. It's a typical thing. It involves getting up out of a chair and doing other functional tasks. She increased that by 1/3. She improved, for example, this speed that she could walk 31 feet by nearly 50%. So even in a 105-year-old who is already suffering quite a lot in terms of function, with an appropriate physical activity or exercise intervention, you can see enormous changes in just a tiny amount of time. So it's never too late to start. And the other good thing is that a little can go an extremely long way. We developed this concept of something called exercise snacking. This was Ollie Perkin. He was one of my PhD students a few years ago. We did a little segment on the TV for Trust Me, I'm a Doctor, looking at how you can maintain muscle mass in later life. And based on some of the work that Ollie did in his PhD, we developed this concept of exercise snacking that people could do at home. And it involves very, very simple exercises. So literally getting up out of a chair repeatedly several times a day, a few days of the week. And if you look at this link, or I can send this around or share it with you, you can find different types of exercises that you can do as part of this exercise snacking. So you don't have to go to the gym, you don't have to start lifting weights, you can do things just using your own body weight, and it will have a very positive effect on your muscle strength, your muscle function. And if you keep your muscles happy, it will keep the rest of you happy as well. So take-home message number 4. Regular physical activity dramatically improves aging trajectories. So if you're just active, as we talked about that earlier on, it will change what happens to you over time. If you've left it a bit late, it's still not too late. There is something that can be done. Even people in their hundreds will gain a lot through changing their physical activity. And then just on that final point, a little goes a long way. You might, if you want to increase overall energy expenditure, you might need to do quite a lot of physical activity. But if you just want to change function, you want to improve muscle strength, actually, this exercise snacking concept is remarkably effective. So I think I'm about out of time. So this is just a cartoon I want to finish with. I'm sure you've heard much of this before. Exercise, exercise, exercise. I probably would change that to physical activity. I sometimes think that when I talk to people, this is what they say in response, or perhaps what they say in their heads, but I'll leave it up to you. I look forward to having some questions. That's where I'd like to finish. Thank you very much.
Do you think genetics comes into this as well?
Absolutely. I mean, there's no doubt that genetics makes a big difference. I mean, and some of that might be in surprising ways. So it might influence things which then influence your ability to regulate muscle mass, for example. So for this ATOMA study we're recruiting at the moment, we are recruiting people and finding quite big differences in the production of inflammatory molecules by adipose tissue. And these inflammatory molecules seem to be affecting the people's ability to regulate muscle mass. So there is perhaps something going on genetically within adipose tissue, which is influencing the ability to maintain muscle mass, for example. But yes, no, genetics definitely affects your physiology, your fundamental physiology. It will affect how you respond to physical activity or exercise or diet. So there's no doubt at the end of the day, you can't change your genes. They're born, that unfortunately that's nothing you can do about. Everybody will still gain and lose depending on whether they manipulate physical activities, just by how much. That's thank you.
On your second graph, which was the dose response for exercise,
Yes.
the increasing exercise decreased the morbidity or whatever, but at a certain point it started to rise. Why
That's
is that?
very well spotted, and actually that's a consistent finding, actually. And in some studies it increases by a bit more than that graph. So there's been a lot of debate about that. Is this a case of people potentially doing too much? It absolutely could be. I mean, at the end of the day, it is a stressor. You are stressing your body. If you are training 30 hours a week, which some people can be doing, that may well be more than our bodies are expecting, and therefore you're going beyond what would be considered an appropriate stress into a kind of pathological or unhealthy stress. Certainly could be that. Some people have pointed out that the sample size, once you get to those very high levels, is much, much smaller. So the confidence in the estimates is also much weaker. So I think if you get a group of epidemiologists in the room, they will argue about this for a long time and probably never agree. But it's a consistent finding, but we don't really know why. But well spotted. That was only up for about 30 seconds.
Looking back at the European Space Agency 60 days of bed rest,
Yeah,
and the detrimental effect, did they go beyond that and see how long it took to reverse that?
that's a really good question. So, for this study, it was an incredible study, really. So they had to spend 2 weeks in the facility beforehand, where they have a variety of different tests. Then they have the 2 months in the facility. At the end of the bed rest, they can't even stand up, so they can't support themselves. So they stay in the facility for another 2 weeks, and they get to the point where they absolutely can look after themselves within that 2 week period. And muscle comes back very, very quickly, actually, within just a few weeks. But they have followed them out for even a year later. And what they found is that bone actually, it's interesting as a graph, it goes down a little bit during the bed rest. It then carries on going down for a few months afterwards and then starts to recover. Even a year later, it hasn't recovered. And that's why in these bed rest studies now, they don't do the studies in women, they only do them in men, because women have lower bone mineral density anyway, and they don't want to put them at any disadvantage of increased risk of osteoporosis in the long term. I don't know if they've followed out for longer than a year. So whether it ever recovers or whether it just stays a bit lower, I don't know. But most systems recover quite quickly, but with the exception, as far as I'm aware, of bone, which seems to take an awful long time to recover, or it doesn't recover at all.
Yeah, I'm really involved in cancer support and cancer research, and a common thing you see during cancer treatment is fatigue, immense fatigue, and people lose. Also, I actually put on loads of weight, but that's inactivity. You can't do much, and then you're very weak when you finish that. And there was a program to across the country for rehabilitation, and for funding reasons they dropped it, which I think was a very poor decision, because the recent study, the challenge trial, showed that 5-year survival rates 37% increased if you have the standard 150-minute exercise program. So that's more powerful than most drugs used in cancer treatment. But they look at a number of factors, and what you described there with the space thing is that during chemotherapy, your fitness, your capability goes down, and then when it comes, if you do the rehabilitation, it never quite comes back to where you were. And within that, they talk about sarcopenia, which you've explained there, and also cachexia. And is cachexia a reversible thing? Is it a thing that is it working in the same way as sarcopenia?
Yeah, I think it does. But you're absolutely right that fatigue is a real problem. I mean, we've done a couple of studies in women with breast cancer, and trying to support them both during treatment and after treatment, actually, and including using things like wearable technologies to try to change overall levels of physical activity rather than saying you've got to go to an exercise class, because it's much easier to do a lower level of activity and build up the volume than it is perhaps just go out and do something more intense, for example, which might feel harder. So, no, but I think it is reversible. So I think the cachexia just accelerates the changes in a very short period of time. But once people are better, you can gain muscle in just the same way as people who have sarcopenia, people who've lost a lot of muscle, the people after bed rest. Younger people will find it much easier than older people because of this anabolic resistance. But it is possible.
I've got a question from the internet.
Oh, right.
Someone going under the name of Dell. Is regular yoga or Tai Chi 3 times a week for an hour good enough, or should exercise include cardiovascular exercise?
I would say it probably depends what you want, ultimately. I mean, yoga and Tai Chi is very good for mobility and function. It's good for balance. We had a Taiwanese student, and she did a lot of her PhD on Tai Chi in older people. It's extremely good for balance. The effects actually seem to be not that different to the exercise snacking model. We did a comparison of the exercise snacking I presented compared to Tai Chi, and it seemed to be reasonably similar in terms of effectiveness. If you want to reduce your risk of cardiovascular disease, heart disease, I would say it probably wouldn't do as much to change that. It probably wouldn't do as much to reduce your risk of diabetes. So it really depends on what outcome you're looking for. So I think the different forms of physical activity, and we didn't have time to get into that, but the different forms of physical activity can be used depending on what you want to get out of it, and different things will suit different people.
We get bombarded with suggestions about improving our mental acuity. Is this all balderdash, or is there something that you can actually kind of endorse?
In terms of mental training, you mean, or do
Yeah.
you mean the link between physical activity and
Apps to do puzzles on the computer or
Oh, yeah.
on the phone and so on?
I don't know. I don't know the evidence well enough to know whether I suspect that doing these things will have a positive effect, but I've never read the literature, so I really wouldn't know. What I can then say, though, is that there is evidence that physical activity and exercise improves cognitive function and outcomes in older people. So we didn't get a chance to talk about that, but everything from general cognitive function through to risk of Alzheimer's is reduced with appropriate levels of physical activity.
Good question.
Yeah.
One is to go back to what was mentioned earlier about the tick of the end of the end.
Oh, yes, yeah.
Is that partly extreme exercise, and is that partly extreme athletes? So is that the cyclists and the footballers that suddenly got dead in the middle of?
So I mean, I think most of the cases when you have the footballers for dropping dead, there's usually an underlying pathology which has led to them having a cardiac arrest. So I think it's not that, I don't think, but I think it's more that these people are doing really extreme levels. I mean, they can easily be doing 30 hours of very high intensity training a week, which I think is just placing such a stress on the body that it's the systems which are trying to respond, which are all the good things are coming from, have been overloaded to the point where you're seeing a deterioration in good health. But I would say, I still would emphasize that I think the jury is out on exactly what's happening at that end of the curve.
I remember a long time ago talking to a GP about running, and I thought a couple of miles a day. Right. He said no, 20 miles a day.
Oh, okay. Wow.
And to go back to what you said about we've evolved to be to expect exercise. And thinking about the Ethiopians who are superb marathon runners. He said, in places like Ethiopia, traditionally, they would run 20 miles a day to get water.
Yes, I mean, I think there are some, and again, I didn't get time to go into this, but there are some fascinating comparative studies looking at indigenous populations who live lives very close to hunter-gatherers today. And if you look at their levels of physical activity, it is enormous. And if they don't get some kind of infectious disease, they will live in the absence of cardiovascular disease, the absence of diabetes, into old age with these very high levels of physical activity. So I think these studies are great. There's a really good book written by Dan Lieberman called Exercised, and it's a brilliant text, and it goes into many of these comparative studies, and it's written in a really accessible way. So if you want to read more about that, you could maybe look up that book. Yeah. Yeah.
Earlier on, you were talking about things which reduce the so protein and uptake of protein. So can you, to some extent, compensate rather than protein?
I'm really glad you mentioned that, because I actually meant to mention that when I showed one of the slides. So I don't know if many of you are.
We can't.
Yes, sorry. Yes. So the question was, can you compensate for this anabolic resistance by eating more protein? And I did mean to mention that when I was showing some of those studies. And the answer to some extent is at least to a point. So I don't know if you're aware, but the recommendation in terms of protein intake for older people is actually higher than it is for younger people. So as you get older, you should be eating more protein because of this anabolic resistance, to try to at least partially offset the fact that you're not getting as big a response as a younger person would. It isn't completely effective, but it is at least partially effective. That doesn't mean you need to be, it's not extreme levels. I'm not talking about buying protein shakes and all these kinds of things. It's just increasing protein intake. And actually the fact of the matter, unfortunately, is that actually protein intake usually goes down as people get older. So you should be aware of that if you're concerned about the protein intake.
So Dylan,
Yes.
your exercise and consuming protein ought to increase your health span. Is there any evidence that it increases your lifespan? Let's live longer, because the oldest living lady, I think she died in France about 125. You seem to do that, yeah.
No, Jean Calment. I think that comes back to the genetics question. I think she also smoked. Probably something you wouldn't advise. I think that's a great question, and I would say the evidence for health span and the evidence for getting to your 70s and above 75. So many of these epidemiological studies, probably wrongly, consider that if you get to the age 75, you've lived a full life. And they say that's, we don't even count that as mortality, actually. So the evidence about getting to 75 and getting to 75 in good health, with good function, and being able to live independently is incredibly strong. I think longevity is a different issue, and I think actually I think the evidence is much more equivocal about longevity. It will add, and there's a little, I can't remember the quote, it will add life to your years, not years to your life, or something along those lines. So I think that's probably the best way to think of it. I suspect it will certainly not only make your life more comfortable. I suspect there will be a longevity effect, but just nowhere near as big as the health span. I mean, you're probably talking a year or two or something like that, rather than the decades that it would be in terms of health span. Great question.
I'm heavily involved in Cirencester Park Run, and we have many older runners. Your implication was that resistance training is what you need to defeat sarcopenia. And do I therefore take it that cardiovascular doesn't really help?
So I think cardiovascular, things like running, is great for things like balance. It's really good for maintaining, obviously, muscle mass in your lower legs, maintaining it. It won't increase it very much, but it will maintain balance, it will maintain strength for normal function, and it will make the muscles able to do some of the other things I was talking about in terms of releasing molecules into the blood which affect other systems and taking sugar up and things like that. It won't do some of the things that resistance training is doing in terms of increasing muscle mass if you're sarcopenic or low. It will probably just maintain it, stop it getting much worse. So and it won't do anything to your upper body, for example. So things like grip strength and ability to open jars and things like that as you get older probably won't be affected. So probably you want to do a bit of both. But that doesn't mean you need to start going to the gym. Like I said, you could use these alternative strategies which you can do at home. Yeah, I tell you what, you guys should come to some of my conferences. Because just go to the conferences, you can get 1 or 2 questions if you're if you're looking. So yeah.
Chris, can you check that the microphone's turned on?
So I wanted to ask a question about cultural movement and how do we, like we're all sitting around, we've been sitting around for an hour and a half, and when we're at school as children, we're told to sit, which used to drive me crazy, absolutely crazy. I used to gaze out the window, what have I done wrong, why can't I go outside?
Yeah.
So culturally, how can we change our habits, change our culture, so we end up being more like Bushmen?
Yeah. So I'm a physiologist, more a biologist essentially. I don't have an answer to that question, unfortunately. I wish I did. I know that when I go to conferences that I go to, we build in activity breaks. So you wouldn't be sitting for an hour and a half. You would have to get up. You would be doing other things. A lot of the people would actually be standing at the back of the room because they don't want to be sitting down. So I think some of this can come from within, if you know, so maybe information helps and knowledge is maybe power, that kind of thing, perhaps. But systems change, policy change. I mean, I think schools is a really good example. I mean, we've got a paper coming out, the biggest analysis of primary school children in the UK using wearable devices, 17,000 children. In England, they've all got the same curriculum. The teachers have been through the same education system. They've got the same resources. They get the sports premium to support physical activity in primary schools, all of these kinds of things. The level of activity in primary schools, assessed over 25 days, so it's a very long period of measurement. The level of physical activity in primary schools can vary by 8-fold. And so that's something about policies and ethos within the school and attitudes of teachers, head teachers, the way they've designed the school, those kinds of things. It wasn't influenced by playground space. So just because you've got a bigger playground doesn't mean you've got more active kids. It was something to do with the way the school was operating. So what those head teachers are doing, or the teachers in those schools, is something which is having a massive impact. We don't know what it is from that study. We just know that there's a big difference. So it can be done. You can do things to change things, but that's somebody else's area. I can't really comment on exactly how we could do that, but I'd love to see those things happen, because I think it would, as you can see from my interests, it would have a huge impact. So,
have you considered the impact of trauma on the physiology of the muscles?
Yes, and so that catabolic crisis model is part of that, actually. So those big decreases that you get in terms of muscle mass very acutely. It's not just the inactivity, it's because of inflammation, trauma, the changes within your body, inflammatory cytokines, which are leading to changes within skeletal muscle. So physical trauma, yes, that would be part of
mental
that.
trauma as well.
Mental trauma, yeah.
I'm a physiotherapist and I've specialised in trauma treatment for the last 30 years. And the impact of trauma impacts the functioning of the soft tissues. And they tighten and they don't work.
Oh, yes.
The body adapts to the trauma.
And you're talking about mental trauma. Yes.
In the tissues.
Yes, yeah. That's not something I know about, but I could imagine how it could, and I could imagine how it would change the spontaneous
it can have a
movements.
huge impact
Yeah.
on somebody's life
Yeah.
if they have a major trauma. And many people coming to physio departments with pain, when you go back, you find it relates back to quite a significant trauma. It might be surgery, it might be a road traffic accident,
Yes.
it could be many, many things.
Yes.
And I think this is an area that needs looking at.
No, I think that's a really good point, and perhaps calling for more rehabilitation and so on strategies around
With an
trauma.
understanding of trauma.
Yeah, I certainly, I mean, so we did some work with the weight loss clinic in Taunton. And one of the things that, so this was people with very extreme weight problems who were waiting for bariatric surgery. And many of the patients who were waiting for surgery, they could, the doctors could work out eventually that this was triggered by some traumatic event at some point. And so where they got to at that point was influenced by a key moment in their life, which often wasn't a physical trauma, it was something that happened to them or their families.
It can be both,
Yeah.
but it can have an enormous impact if the trauma is unresolved
Yes.
on their physical well-being
No,
for years to come.
Yep, I absolutely can see how that could be. Yeah.
Right, we have one more last question. On the internet, I think.
Oh.
Thank you. Another question from the web. Bit of actual real advice requested. The easiest form of regular physical activity to organise around your daily life is probably walking. Would you recommend walking, aiming for say 30 minutes a minimum every day to reduce the risks of inactivity?
I mean, I think that's a great question. And I think I would say that walking for 30 minutes is fantastic. If you walk for 1 minute 30 times, it's probably just as good. So if you wanted to spread the activity out over the day for certain physiological systems, that could even be better. So for glucose control, for sugar control, little bits of activity spread out a day would probably be better than one big bout. But if you want to gain muscle mass or cardiovascular changes, probably the bigger bout would be slightly better. So, but yes, I mean, I would say walking is a brilliant mode of activity. It's probably closest to what many of our hunter-gatherer ancestors would have done. We would have done some running as well, but a lot of the time it would have been walking long distances. So building more walking into your life is brilliant for that. If you want to do brisk walking, that's going to be, there are some additional benefits to that, but just walking, even not briskly, will carry some very positive effects on health. So yeah, walking is fantastic. Yeah. Did you say there was no? Okay.
Yeah. We're very used on a regular basis to standing on a weighing machine and weighing ourselves, but we're not used knowing exactly how much activity we've taken on a daily basis. You showed an expensive device now, the smartphone,
Yeah.
smartwatch, which tells the amount of activity in terms of pace that I'm taking.
Yeah.
Today. Is there something that you think that we perhaps as people, as we grow older and as time goes on, we will have a measure that we can reach to every day and say, yes, I've had enough activity. If so, what will it?
That's right. I mean, so actually we've done a lot of work for, which the Consumer Association. So for many years we were doing their reviews of wearable devices. So we were doing all the testing to compare to see how well they worked and whether they measured what they were claiming they were measuring. And we would then give the data back to which, and they'd write up their reviews and so on. And when we did a lot of that work, some devices came out incredibly well. And so one of the ones which came out consistently well was an Apple Watch. The Apple Watch seems to work extremely well compared to many of our research grade devices compared to our laboratory measures. You can get a measure of volume, which would be close to energy expended through physical activity from the Apple Watch. Some other devices were awful. I mean, really, really awful. There was one that was produced by Microsoft. And on the packet, it looked amazing. It had 10 sensors within it. It was claiming all these amazing and wonderful things. We tested it, and it was the poorest performing out of all of the devices. The review was then put online by which, and literally within months, they discontinued. Because I think they knew it was rubbish. So I would say, shop around, read about the different devices that you can afford within your budget. Some do work quite well and will give you the kind of information you're looking for, which is a volume type activity. But if you're looking for if you don't want to do that and you don't fancy the tech, you could just build things into your life and just assume quite reasonably that it will have positive effects. So this exercise snacking, you probably don't need a device to measure that. You can just do it and it will have positive effects. So I think it depends if you fancy that kind of thing or not. I quite like wearable technology, but lots of people don't. They find it a fact. So yeah, great question.
Right, I think we really ought to wrap it up at this point.
It's been a great evening. Professor Thompson, thank you so much.
Yeah, and thank you for the questions. Very, very stimulating. So very useful. Thank you.